This is Statistics 243 at Berkeley for Wednesday, December 3rd. Okay, let's go ahead and get started. All right, so we have a little bit to finish off in terms of talking about integration, and then we'll start talking about graphics, in particular looking at some examples of critiquing some graphics. So I thought I'd say a little bit more about this Newton-Coates quadrature, which we already saw is basically the kind of integrals that you've already seen in calculus in terms of things like the trapezoidal rule and Simpson's rule. Romberg quadrature, which is also known as Richardson extrapolation, which is a special case of Richardson extrapolation, is basically using some of these sort of basic ideas like from the trapezoidal rule, but in a sort of clever way to get more accuracy with fewer calculations. So in terms of sort of the trade-offs that go on computationally when you're doing this, the more times you have to evaluate the function, then in general you're going to get more accurate estimates of the integral, but you also have to do more computation. So there's that trade-off. So the idea of Romberg quadrature is to basically sort of cleverly choose the approach you're going to take, and then the result of this is you actually get higher accuracy. So suppose I define a little bit of notation. Suppose that for a given interval length h, so remember I'm splitting up, I have some region over which I want to estimate an integral, and I split it up into little subpieces of length h, and there are going to be n of these. So I could define the trapezoidal rule on if I have intervals of length h. Right? I'll just end up with sort of the usual picture with sort of trapezoids, the piecewise trapezoids. And if I did that, I would have to do, I'd end up doing n evaluations. Okay? But I could also think about doing, well, let me take h and make it h over 2, and let me use the trapezoidal rule using h over 2. And in that case, I would have to do 2n calculations, because I'd have to do the calculation at each of these points. So the x's come in if I'm doing it at h over 2. But sort of the cool thing that someone or another figured out at some point about this was that if you take this combination of the trapezoidal rule with h over 2 minus 4 times that minus the trapezoidal rule with h and divide by 3, that you actually get a sort of higher order in terms of accuracy estimate of the integral. And the reason is basically what I wrote up here, which is we know that the error of the trapezoidal rule is order of h squared, so it depends on the length of that interval h, of the interval lengths h. So if that's the case, we could write, it turns out that you can write out the error between the estimate of the integral and the actual interval, which I'm calling integral, which I'm calling t here, as being a constant times h squared plus order of h to the 4th. So turns out there's no h cubed term here. And so if we just take this error and think about that same error, but now with h over 2, we then, instead of h, we have h over 2 here, so we have the same constant times h squared over 4, plus we have some term that's order of h to the 4th still. Okay, and I haven't written out the constants here. But if you notice this and then say, well, I could just cleverly take 4 times this minus a single 1 times this and divide by 3, well, what that means is t hat at h is going to be equal to t plus this, and t hat at h plus 2 is going to be equal to t plus this term. And so if I then subtract this, these two terms, what I get is I get 4 times t minus t over 3, because I've moved the two t's to the other side and multiplying 4 times this one and just 1 times this one. And then I get 4 times this error term plus an order of h squared, where the 4 disappears into the order of h to the 4th, because that's just a constant when we're thinking about it in terms of the order of magnitude. And then I'm subtracting off my expression for t hat, which is t plus this. Or sorry, I'm subtracting off my expression for t hat, which is t plus this business here. So I get minus c1h squared plus order of h to the 4th. But of course, since I've chosen 4 here, these two terms, sorry, this is not 4, this is 3. These two terms cancel, so I've basically killed off the order of h squared error term, and all I'm left with is an order of h to the fourth term. So, so what we see is that my new estimator should be equal to the true integral plus an error that's order of h to the fourth. And that's just because I sort of work through sort of the details of what the error functions look like and what they were in terms of functions of h squared and h to the fourth. So it turns out this is actually going to give you the same result as if you'd done Simpson's rule with intervals of h over 2. So I just said if we'd done the trapezoidal rule with h, we have to do n calculations. Now if we do the trapezoidal rule with h over 2, we have to add in another n calculations at the midpoints here. So when I do it with h over 2, that's n more calculations or evaluations of the function. So this is going to be 2n calculations altogether. But if this is this is going to be equivalent in terms of error to doing Simpson's rule, but with h over 2. But in terms of Simpson's rule with h over 2, so here's h over 2, here's h over 2. But of course, with Simpson's rule, we have to evaluate the function not just at the endpoints of the intervals that are of length h over 2. We also have to evaluate the function at the midpoint of the interval. So I would also have to evaluate it at these points here. So if I evaluated it here, 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 and here, that would be the same as here, 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 here. So that would be 2n calculations. But then I have twice that many because I have to do it at these midpoints. So that becomes 4n calculations. So this approach basically allows you to get the same order of accuracy, but with half as many calculations as if you'd actually explicitly done Simpson's rule. So in some sense, maybe the details of that are not all that critical, but the points I wanted to draw out was this idea of trading off how much computation you have to do to get a given amount of accuracy, and this idea that this comes up in other contexts in statistics of sort of killing off components of the error, which we saw over there. Okay, any questions, comments? Okay, so these are Romberg quadrature and more generally this Richardson extrapolation are good techniques, and you if you went to go look for software that implemented them, there should be software out there. It turns out that in R, the integrate function that I showed you, I think last time, actually uses something called Gaussian quadrature, and we're not going to go into a huge amount of detail because sort of the details of this get a little bit complicated fairly quickly. But the idea of Gaussian quadrature is that if you want to estimate this integral, and you notice this is an integral with respect to some probability density mu. That is, if you cleverly choose the points xi at which to evaluate the function and these weights wi, it turns out you can get a good estimate of the integral this way. And it turns out that this approach to estimating the integral using this approach called Gaussian quadrature can actually exactly estimate polynomials up to degree 2m plus 1. So depending on the number of points that you choose m, if the function is either exactly a polynomial that is of order 2m plus 1 or lower, or is approximately, it could be approximated by a polynomial of that order, then this approach will do a good job there. On the other hand, if the function is sort of more wiggly and couldn't really be well approximated by by a polynomial of this order, then it may not be all that accurate. And so part of the idea here is, and we'll see this also with this adaptive quadrature, is when we're talking about just the standard Newton-Cotes quadrature like trapezoidal rule and whatnot, we had these intervals, but the intervals were always the same length, and the spacing of the points that we evaluated was the same. But if we had some function that was sort of wiggly in some place and then smooth somewhere else, and we wanted to calculate an integral of that, well, it doesn't really make sense to have intervals that are the same length throughout, because over here it's sort of almost linear, and over here it's changing very rapidly in this part of the space. So having these equally spaced intervals doesn't help us, is maybe not the best way to go. So in terms of the Gaussian quadrature, what happens is these nodes, these xi's, the points at which you evaluate the function, cluster in areas of high density of this probability density. And more, if you go even further in terms of taking an adaptive approach, you would basically choose where these points are and how tightly clustered the points are based on how wiggly the function is in different parts of the domain. So that would be an adaptive procedure. So you'd end up putting more points in this part of the space where the function is wiggling more quickly, and you'd put fewer points over here where you'd basically be wasting your evaluations because the function is smooth and well behaved in that part of the space. Okay, so I didn't want to, like I said, obviously that's not very much detail. If you went into if we were to delve into the details, we'd have to go in and investigate these things called orthogonal polynomials in some detail, and that's sort of beyond the scope of what I wanted to go into. But at least to give you a sense of at least sort of vaguely what's going on with some of these other quadrature methods, that's the overview. Okay, let's see, questions about that? Yeah, Lei?
So what's the difference of doing this quadrature rather than doing the simulation? I mean, simulation can also give us like approximation to the integral, right?
Yeah, so that's actually sort of what we're going to see in a second, is this idea of how it scales with dimension. So the general rule of thumb, which I mentioned last time, but is good to repeat, is that for a given number of function evaluations, if you have a low-dimensional integral, particularly 1 dimension, 2 dimension, maybe 3 or 4 dimensions, you're better off using these quadrature methods. And if you have a high-dimensional integral, you're better off using Monte Carlo integration. Okay? And what we're going to see next is sort of some intuition for why that is. Yeah. So okay. So all right. So to start off with that, let's sort of go back and think about Monte Carlo in the Monte Carlo estimation of expectations or integrals a little bit more. Okay, so what did we work out last time, or not last time, what did we work out when we were talking in the simulation unit about Monte Carlo integration? We said we had this estimator that was 1 over m, the sum of h of xi from I equals 1 to m, where we had drawn xi from some density f of x. And we said this was a Monte Carlo estimator of the expected value under the density f of the function h of x. And we had also worked out that the variance of this thing, so I'm going to call this thing, let's see, do I use any particular notation here? Maybe not. Maybe I'll call this thing t hat, because that's sort of like the notation we're just using. We worked out that the variance of t hat was 1 over m times the variance of h of x. Okay, so this thing, if we now think in terms of standard deviation, the standard deviation scale, which is sort of the scale that we usually think of errors being on, we have that the error for t hat from the Monte Carlo estimator is order of 1 over m, order of the square root of m. Sorry, order of 1 over the square root of m. Okay. So order of m to the minus 1/2. I think I'm going to, since I threw m in here because that's what we used in the simulation unit when we were using notation, but I'm going to change this right now to n because I used n for the remainder of this. So to try and standardize my notation, let's assume now that we were using n as the notation to denote the number of samples that we took from the density. Okay, so this is order of n to the minus 1/2. Okay, so we'll keep this in mind, and now let's think about, and there's nothing in here about dimensionality. So nothing in here says that this isn't going to, this order of the error is not going to change as we're doing if x is 1-dimensional versus 2-dimensional, 3-dimensional, 4-dimensional, etc. So we'll come back to this in a second, but now let's think about what happens if we're doing quadrature and we start to go to higher dimensions. So if you think about it, we divided up our domain in one dimension into intervals of length h, and we said there are going to be n of these points at which we evaluate the function. Say we evaluated each of these, we're evaluating each of those points there. Well, now let's think about what has to happen if we go up to 2 dimensions and we're evaluating an integral. Right? So this was, we're evaluating some integral that looks like that. If we're in 2 dimensions, and there's some function coming out of the board in 3D at us, what do we have to do? Well, we have to break up our domain into little boxes. So now instead of intervals, we sort of have these little boxes over which we're going to do some sort of estimate or approximation of the integral for each of these boxes. And so we could, for example, just choose the same h over there as we did here, and then we're going to have n here and n here. And so if we evaluated each of these corners of these grid points, we're going to have done n squared function evaluations. So here we would have done n evaluations. Here we would have done n squared evaluations. You can imagine if we go up to 3 dimensions or 4 dimensions, that we're going to have done n to the d. We're basically going to have to do n to the d evaluations in order to get the length of these little intervals to be the same as if we had, as if in the one dimension, we're in the one-dimensional case. So what that means is, as we go to higher dimensions, we would need to do to take many more function evaluations to basically get the same order of accuracy in doing the quadrature in terms of estimating the integrals. So that's one way of thinking about it, is if we wanted to get the same error, how many more function evaluations would we have to do to get the same error as this dimensionality throws? But the other way of thinking about it is, suppose we have a fixed budget, we can only do, suppose that we know how long it takes to evaluate a function, we only are patient enough to do n evaluations. So if we're only patient enough to do n evaluations here, and now we think about allotting those n evaluations over here, that's going to be equivalent to doing the square root of n and the square root of n basically in each dimension. And so our h is going to have to get much bigger in 2 dimensions than it was in 1 dimension. Or it's going to get much bigger in 2 dimensions than it was in 1 dimension if we use the same number of function evaluations n. And it's going to get even worse as we go to 3 and 4 dimensions in terms of the effective number of samples, number of function evaluations that we've done. So here the effective number of samples that we've got is n to the 1/2. And as we go to higher dimensions, the effective number of samples we would have is n to the 1/d. So this is just sort of the flip side of saying that to get, we go from n to n squared to n cubed, or n to the d. If we think about it as a fixed budget n, the effective number of samples we have in higher dimensions scales as n to the 1/d. Okay, so questions about that?
Here we still evaluate for n times. So what do you mean by the effective number of evaluation is n squared?
Yeah, okay, so maybe that's a good question, because maybe I was sort of saying that in a bad way. Right, we're still doing n evaluations, but if we, let's see, a better way to put this is that we had an error, if we have error that's order of n h to the q here. So for example, trapezoidal rule would be order of h squared, Simpson's rule would be order of h to the 4th. Here, basically, h is proportional to 1/n. So for example, if we had h would be if the endpoint here is a and b, then we could compute h as b minus a over n. So h and n vary inversely. So that's all I'm saying here is h is proportional to 1/n. So if the order of the error is order of h to the q, here the h is scaling as h to the let's see. I don't want to say this. Maybe this is the best way to say it. So the error is the error is order of h to the q, and we know h is proportional to 1 over n. So the error is proportional to is order of 1 over n to the q. But the basically the effective the number of effective samples in a given dimension is scaling as n to the 1 over d. So I guess maybe that's sort of what I was trying to say back when I was writing it this way, is here I had n samples with respect to one dimension. If I still want to only do n evaluations, what's going to happen here is I basically have sort of equivalent to the square root of n, basically square root of n effective evaluations in any given dimension. So the result then is I've got order of n to the minus q, but now once I introduce dimensionality, I'm going to have order of n to the 1 over d, and then to the minus q. So hopefully that helped a little bit. Other questions about that? Okay, so this is order of n to the minus q over the q we can think of as being fixed, because that just depends on what method we've chosen to do the quadrature. So maybe we chose to use the trapezoidal rule or chose to use Simpson's rule or whatnot. But now let's go ahead and compare this to doing Monte Carlo estimation. So n still means how many function evaluations do we do? And this says, well, the error looks like this. Q is going to vary depending on what approach we chose, but it scales as n to the minus 1 over d, and this scales as n to the minus 1 over 2. So as d gets large, so you can imagine d might be 10 dimensions, say, this is going to scale much more poorly than this is going to scale. So basically, if we think of what we're doing in terms of the error and changing n with Monte Carlo estimation, well, as we go up to, so suppose n were 100, this is going to be something like 10. As we go up to, say, 100,000, this is sort of not going to be, not in very good proportion. But we're going to get something that scales like this in terms of the error. So we get sort of decreasing returns as we increase n. I mean, that's the usual story with increasing sample size, just in any statistical problem. But it is increasing, and we have this rate of 1 over of n to the minus 1/2. I guess I should have drawn this as 1 over n to the minus 1/2, but hopefully you sort of get the sense of what I'm trying to say here. But if we look at this, as we increase n, we're not going to get as much bang for our buck as we increase n in this situation, because we have n to the minus 1 over d instead of n to the minus 1/2 here. So let's see if there's a useful. So yeah, if we were just to look here, okay. So another way to think about this is just to sort of plug in some numbers and see what we get in terms of results. So suppose d were 10 and we had 1,000 function evaluations. Well, we can think of this as being equivalent to having an n. If we were the accuracy is if we were working in one dimension and we had 1,000 to the 1/10 as many evaluations, which is only about 2. Okay, so what I'm saying is, if we were to do 2 function evaluations in one dimension, that gives us basically the same accuracy as if we did 1,000 function evaluations in 10 dimensions. So that's sort of another way of sort of looking at this idea of these equivalences. So that's sort of another way of thinking about how this scaling works is sort of the effective sample size in each dimension, which is sort of what I was trying to say over there. And even if we only had a smaller d, for example, 1,000 to the 1/4 is only 6. So that's not very many function evaluations, equivalent function evaluations in one dimension. Let's see, do I want to say anything else about this?
When would there be situations where you can integrate in R instead of mathematical table? Like if it was inside a function or something?
So we're basically, if we can't, I mean, you could certainly do, I'm sure Mathematica has the capability to do this sort of numerical integration. So you could certainly do it in Mathematica, but if you were doing a whole bunch of the rest of your workflow in R, then you'd probably just want to do this in R. So for example, if you were trying to maximize some log likelihood where you wrote the log likelihood like I did last time, I had some, I forget exactly what I had. I had some f of x given some parameters, beta and some random of xb, and then I had some pi of d, db. If I wanted to try and do this integral and then maximize this integral with respect to beta, then at each step of my maximization, I need to basically estimate this integral with respect to b and then do the next step in my optimization. And so I might be doing all of that in R, and therefore want to try and do this numerical integration in R. Certainly if you were just, Mathematica provides also the ability to do symbolic integration. So if you're just trying to integrate some function that's not in the sort of numerical context, you might use Mathematica for that. Okay. Yeah, another question? Yeah.
So why the error increase with n?
Oh yeah, so that was just me sort of, I think, being confusing about what I was graphing here. The error scales as order of n to the minus 1/2, not as n to the 1/2. But I was having trouble thinking about how to graph that. So I was trying to just, this graph was just supposed to indicate this idea of sort of decreasing returns to scale. That as you increase, maybe another way to put this is, so I've got 1 over n to the 1/2. I want this to get as big as fast as possible so that the error gets small, because this is in the denominator, right? So if I want this thing to get small, so I want this thing to get big. But the problem is, as n gets bigger and bigger, I have these sort of decreasing returns to scale in terms of how n to the 1/2 grows. That's, yeah. So that, I think maybe hopefully that's a clear way of saying what I was trying to say a minute ago. So yeah, so we're interested in 1 over n to the 1/2, but this is sort of thinking about how the denominator scales as a function of n. And ideally, we'd like this thing to go up much more quickly than that. And if we have n 1 over n to the 1 over n to the 1 over d, then this is even worse. Like, if this were d equals 10, then we presumably have a plot that looks, I don't know exactly what it looked like, but it looks something like that, where it's not increasing very fast. And again, the same idea. We want this in the denominator to get big. We want this denominator as big as possible. So, but as we increase n, we're not really getting a very, very effective increase in our denominator because of the fact that we're raising n to the 1 over d. Okay, any other questions? All right, so R provides this integrate function, which actually uses an adaptive version of Gaussian quadrature, so it sort of does this adaptation here, as well as doing that whole business with orthogonal polynomials that I mentioned. I don't want to go into this in too much detail, but here's an example. You give it the function, so we know what the integral of a normal density is. We know that it's 1, so I just used that as an example. We could say integrate the normal density from -infinity to infinity. I'm actually forgetting what the 0 and the 0.1 mean. But you could go ahead and look those up. And it says, oh, well, that integral is 1 with an absolute error of 6 times 10 to the minus 7. It has some method of estimating the error, which I didn't go and look into. Oh, right. This is the mean and the standard deviation of the normal density that I'm trying to integrate, of course. So I need to pass in. I need those additional arguments that define the actual density. I could do it for an even more tightly pointed normal density with a standard deviation of 0.001. It also says, oh, that integral is 1. But things fail at some point if I make it too sharply peaked. And so at this point, when I say use 0.001 as the standard deviation and do that integral, it says, oh, it's 0. And it says the absolute error is less than 0. So obviously something has gone catastrophically wrong with the Gaussian quadrature that's underlying this integration in this case. And we just have too sort of sharply peaked a function for this to be able to work very well. So there's some lack of robustness, obviously, to the to using this particular method as it's coded up in R. But this gives you a sense of how you would go ahead and use the integrate function, and also this idea that you want to sort of keep your eyes open and make sure things don't look crazy in terms of the results that you get. Okay, so I think that's all I want to say about integration. There's a little bit here about cases where you have singularities. So you have functions that say are integrable, but that shoot off to infinity. They're not shooting off to infinity so far that you can't actually do the integral, but there is this singularity here. So there are sometimes you need to use some mathematical tricks to try and do integrals, numerical integrals with functions like that. I won't go into the details of that. And then just to make the point, which sort of goes back to the discussion Julie and I were having, that if you wanted to do symbolic integration, you can do that in Mathematica or in Maple. Okay. All right, so any questions before I switch over to the graphics unit? Okay, so I thought what I'd do with the graphics unit is I have a bunch of details in here on various functionality in R, and I'll hit the highlights of a few of those on Friday. But what I thought we'd spend more time doing, and in particular concentrate on today and at the beginning on Friday, is just see some examples of how you might evaluate a graphic in terms of what are considered to be good best practices or good principles in terms of developing, in terms of creating graphics. So a number of people have thought about this. I've got some references up here. And I have some examples to look at. So in terms of best practices, these are some of the things that people have talked about. You want to have a high density of information to the space that you're using. 3D graphics often don't provide additional information. If you need to express quantities that are in higher dimensions, you can often, obviously we're limited on paper or on the screen to 2 dimensions, but we can often go beyond that by employing color or different symbol types or having multiple panels. We'll see some of this. Using stacked bar plots, which we'll see, maybe I'll show you an example on Friday, is often a bad idea. And then one of the main things is human beings often have a hard time comparing areas of things or comparing volumes compared to comparing lengths. So in general, if you're creating a graphic, you want to do it such that you're comparing what the contrast that you're drawing out with the graphic. You want to do that contrast such that people are looking at lengths as opposed to areas or volumes, and we'll see a few examples of that. It's always a good idea to label your axes, and if you have multiple panels, to have the ranges of the axes be the same, and also this a bit that you generally want to have good, nice legends. Okay, so that was very quick. I just wanted to sort of spit out those, but you can go back and look at those as you're looking through a couple of these examples that I'd like to talk about. So the first one is sort of a basic one that I just saw actually in the paper the other day. So this is from, I think it was from the New York Times. It's an advertisement by the Shell Oil Company that is making some point about the growth in urban populations across the world. And it says the rising cities, the population of the world's cities will increase by 2.7 billion by 2050. Nearly 90% of this growth will take place in Asia and Africa. And then it presents a graphic to try and illustrate this. And so what I want to do is have you guys take a minute, 30 seconds or a minute, look at this and try and critique it from the perspective of those principles that I just mentioned. And I will say, it's sort of easy pickings to pick on a graphic that comes up in the newspaper that's not meant to be sort of a scientific or a statistical graphic, but I think it's sort of a useful way to sort of illustrate some of these principles, to see some of them being violated in action. So this is the graphic. Take 30 seconds or a minute. Feel free to confer with your neighbors. See what you think about this graphic and what are the things that are not.
Is there some bottom text you should maybe see?
Yeah, I don't think there's much down here. It's just indicating which of the different regions. So Sub-Saharan Africa and India sort of fall off the page here. Yeah. All right, so what comments do people have about this? Yeah, go on.
It's a pie chart.
Okay, so what's bad about a pie chart?
It's a pie chart.
Yeah, okay, but what about it is bad?
Comparing volumes.
Okay, yeah. So a pie chart is either it's just a flat pie chart, and you're comparing areas of pie slices, which is sort of the principle behind this is if it's hard for humans with their eyes to compare areas, pie charts are necessarily asking you to compare areas. This is actually a 3D pie chart, so it's sort of asking you to compare volumes instead of areas, which is probably going to be even harder than comparing areas by eye. Okay, what else is bad about it? Eugene?
So the color is meaningless.
Yeah, the color. So let's look at the color. That's a good thing to point out. They have different colors sort of to make this jump out at your eye, but is there any scaling here that's obvious? I don't know what the scaling of the colors is. It goes from sort of pinkish mauve or whatever that is on the right-hand side to black to gray to light gray to orange. You know, that's sort of the increasing values, but the color scheme doesn't make any sense. Right? It's not in any sort of ordering.
The values don't correspond to the heights. If you have 29% as your highest chunk, and then the next one is 1%, which
Right,
would
so
seem to indicate that that's also significant, but it's only 1%.
right, so I think what they're sort of wanting us to compare is that the 1% size in this direction is very small, and then it sort of gets bigger and bigger as you go around here. But if that's the case, you know, but obviously with pie chart we're sort of thinking about areas or maybe even volumes, and then that doesn't match up here in terms of height versus size. Anything else?
The total is 101.
Oh, is it? that's right. I mean, that's probably just a matter of that they round. A few of them rounded up. So yeah. Okay. Yeah, I wouldn't say that that's a particularly. I wouldn't say necessarily that's an error. Although there are cases where you might see a graphic where you might see a total that's like 105. You're like, how did that happen? Somebody made a mistake somewhere. I noticed one more thing in here, but maybe there are other things. Anything else that anybody noticed? The other thing I noticed was just the heights don't really make sense at all. In the sense, well, maybe this is the same point as we've already made, is that the height of the 1% is higher than the height of these other percentages, and then like the height of the 18 relative to the height of the 29 is sort of totally out of whack. So I don't know. Maybe that's the same point.
What
But
if they don't have all the same base level?
yeah, you can't evaluate the heights in any sort of meaningful way. Okay, so this was not meant to be a scientific graphic, but it did sort of illustrate some of the things that you'll see that where sort of the way the graphic is presented would lead the brain to think one thing, even though what the quantitative information that they're actually presenting is not being well represented by the representation. Did you have a comment, Eugene?
How do you actually do this in R?
Oh, I don't know. It's probably good that we can't easily do this in R.
It just mind-blowing me how to do it in R.
Eugene?
What is the story that the ad is telling?
What is the story it's telling?
I get a feeling that the graphic is there in at least some part to see.
Well, I think they're just trying to say, that most of the growth in these urban populations will happen in sub-Saharan Africa, 29%, India 18%, Asia 17%, China 13%, so on and so forth.
You actually just misread the chart.
Yeah,
Did I?
India is actually 29.
Huh?
This is a poor pie chart.
No,
Wait.
India is big because I actually read the
He said that India was.
Oh, I just I did misread it. India is 29% and sub-Saharan Africa is 18%. Yeah. So yeah, maybe that also indicates either that yeah, that's very unclear. Okay, well we can stop picking on that one because that was not that was just an advertisement. The next one I want to look at is this appeared in. So this was actually a graphic that somebody came up with and that I think was viewed as being a very nice, informative, well-presented graphic. And so it appeared on this website called Information is Beautiful. So I guess I need to, let me see if I can zoom out a little bit. Okay, so this is supposed to somehow indicate something about the gender breakdown on of people who use different websites. And so I'm just going to introduce a little bit because I can't show you the whole thing, but you can see it shows this equality part, this matriarchy part, this patriarchy part, and then down here it says 99 million more monthly female visitors as the total. So I think, and then it also says down here, which is hard to say, rounded U.S. gender figures and worldwide traffic figures. So I don't quite know how to get everything on the same page here. So take a few minutes, confer with your neighbors, and see what you think about this presentation of information, what you think is good about it, what you think is bad about it, how you might modify it if you were making a graphic to try and illustrate the points that are trying to be made here.
I'm on the site additional design. This is only US.
This is a pretty
Rounded US gender figures and worldwide traffic.
This is a result of this maternal and paternal.
Exactly.
So this is a percentage.
This is the
Yeah, and in English, for folks from other countries, matriarchy means dominated by women, and patriarchy means dominated by men. So it just means more men, more women.
It's more of like societal government, like now a system of society or ruled by a woman or women.
All right, so let's reconvene and see what people came up with. So maybe just as a starting point, what do these little people mean?
Each person's a percentage.
Okay, so each person's a percent above 50%, right? So it says, okay, so YouTube, 54% are men, so there's the 54%, and here's 4 more men, representative of each of 4 different percents, 4% more, so 4 men. And here's Instagram, 53%, and 3, of course, pink women in dresses, I guess. So apart, okay, anyway. Okay, so what do people think? What comments do people have?
Things don't understand what.
What is the Y column mean?
Yeah, what does the right column mean? So you mean over here?
Yeah.
Yeah, so
That's the wrong absolute.
so this says million more monthly female or male visitors. So I think this means that Facebook has 155 million more female visitors a month than male visitors a month.
This is scale, right?
Right.
That's the numbers.
Whereas, why does Instagram have so many fewer? Yeah, there are just fewer people going to Instagram. So even though the percentages of men and, well, a better example is Facebook and whatever this Habo is. Right, they're both 58% women, but here there are 155 million more women than men, and here there are 0.2 million more women than men, just because it's an overall less trafficked website. So it's sort of mixing the percentages here with the total absolute number of visitors on the right-hand side. But there is this sort of mixing of not metaphors, but mixing of content here that's down in this lower portion here, which you might not get unless you look really closely, which is that the percentages are based on the U.S., and then the worldwide traffic figures are based on the world. And it might be even worse than that. Like, I don't know whether they're getting the total worldwide traffic as a total, not broken down by men and women, and then applying the U.S. percentages to the total worldwide traffic to get the things on the right-hand side, or if they actually have worldwide both the total traffic and the male-female breakdown. But if they have worldwide both male-female breakdown and the total traffic, it's sort of unclear why they would show the U.S. gender percentages with the worldwide traffic. Yeah, you could go look at the data, but so either they're sort of mixing things up and they're showing you U.S. for one thing and international for the other, which is a little bit strange, or they might actually be using the U.S. gender figures and applying them to the worldwide traffic figures, even though the gender breakdown in other countries might be very different than the U.S. gender breakdown. Yeah, Eugene?
It's also convenient with misleading because what the total percent is a percent. You look at the column percent 4, 7. So it's like how many more percent than half are males, right?
Right.
But if it's 54 males, it means it's 46 females. So there's 8 more percent males.
Uh-huh.
Not
Right.
4%.
Yeah, I guess it depends on what you're thinking about contrasting too.
It's not like how many more males or females. It's more like how many percent over half.
Right, right. Let's just close with one thing, and then we'll come back to this because I'll ask the question next time of how people might have done this differently if they were presenting the same information. But did anybody understand where this comes from? The gray? Like, what's a gray person?
Yeah, that was what I was wondering, is that it has female or male visitors at the top for all the way to the right, and it doesn't tell you in the gray one what that is supposed to
No, there's a dress next to orchid, and there's men next to it.
Oh, okay. So yeah, you have to interpret in the very fine-grained way. Is this a stereotypical female figure or a stereotypical male figure here? Right. So it looks like orchid is 51% female and Foursquare is 52% male. But you have to sort of look very closely to see that, obviously, because we were missing that initially. And the other interesting thing here is, how did this cutoff get made here between 52 and 53, right? Is that based on some statistical assessment of uncertainty of whether it's actually statistically different than 50%? Or did they just sort of arbitrarily make a cutoff and say, anything between 48 and 52 is neutral, and anything greater than 52 or less than 48 goes into the patriarchy or the matriarchy? Okay, so we're over time, so let's quit there. But we'll come back to this. If you have a chance and want to, muse on this and think about how you might do this differently if you were making this graphic.